Today's video is about molecular orbital theory. I want to start off talking about valence bond theory, which is something we already covered, and I want to remind you what that is. The simplest molecule we can talk about is H2, which forms from the reaction of two hydrogen atoms. So valence bond theory looks like this. We take one H atom, I'm going to draw the nucleus as a small dot, and it has a 1s orbital around that nucleus, and that's where the electron is in the hydrogen atom. So we think about, in valence bond theory, one hydrogen atom, like this, and we think about bringing that together with a second hydrogen atom, which also has an electron in its 1s orbital. And in valence bond theory, we think simply about overlapping those two orbitals so that the electrons in those two atoms come together to form a shared covalent bond. So I can think about this in two steps. Right now what I'm going to draw is just the superposition sort of those two atoms in space, and they bring their electrons together. When we take this overlap and draw sort of what that overlap looks like in total, it really looks something like this. So we get a new electron cloud that looks sort of elliptical in shape, and we have two electrons in there, and we call that a sigma bond. Okay, and as we've talked about, a sigma bond is characterized by having a lot of electron density along the bond axis. I'm drawing in with a little dashed line, so along the axis between the two nuclei. And that's valence bond theory. We bring together two atomic orbitals, we allow them to overlap, and they form, in this case, a sigma bond. We also saw ways that orbitals can overlap to form pi bonds. All right, so what's new about molecular orbital theory? Well, molecular orbital theory is much more based in quantum mechanics. There's some quantum mechanics here in that we have electrons in 1s orbitals, and that comes from quantum mechanics. But when we combine the orbitals, we actually kind of threw that out, and we just thought about these things very much as just spatial entities, orbitals that overlap to form a bond. If we go back to quantum mechanics, we've actually done something here that we're not really allowed to do. We started with two orbitals, two 1s orbitals, and we ended up with essentially one orbital, right? One region of space where two electrons belong. And in quantum mechanics, we're not allowed to do that. We are not allowed to lose orbitals, and the technical name for that is conservation of orbitals. So molecular orbital theory, or MO theory, looks to start with a lot like valence bond theory, but then adds something else. So what I want to do, I'm going to leave this up here because actually what we did here, minus the electrons, is part of MO theory. So in molecular orbital theory, I'm going to erase valence bond theory because we're no longer going to do that. We bring together two atomic orbitals and we combine them to form a molecular orbital. So right now all that's changed is the terminology. I'm calling this a molecular orbital, and in fact I'm going to call it something a little more general, which is a sigma orbital. So a sigma orbital is like an atomic orbital, a region of space where electrons can be found. The addition that we make with MO theory is that we have to come up with another molecular orbital. We started with two orbitals, we have to end up with two orbitals. And in quantum mechanics, we do that by taking all possible linear combinations of these two orbitals, which mathematically in this case is pretty simple. We have to add another case, which is this 1s orbital minus the other 1s orbital. Here we added them together. We also have to consider the case where we subtract them. Now I'm going to use another way of showing this subtraction. Subtracting one orbital from the other is the same thing as adding the negative of that second orbital. All right, and I'm going to show the negative by using something that should be familiar to you, which is shading. So I've just done something basically algebra here, which is to say a minus b is the same thing as a plus negative b. And the negative of a 1s orbital is that same orbital shaded, and as you will remember from p orbitals, the shading means that the sign of the wave function has changed. So if I had psi for the 1s orbital has a positive value in both of these, when I take the negative of that, I have psi with a negative sign, in this case shaded. I'm now going to overlap this case of the two orbitals just the way I did here. So if I bring these two together, I get overlap just the same way. Okay, but now one of them is shaded. So this looks different now. If I draw, so here I overlapped two things and I came up with this orbital here. When I overlap here, where these two orbitals actually overlap in space, I'm adding a positive to a negative. And another way of thinking about this is to remember that the electrons that I'm talking about here, the electrons here are waves. They have a wave function. So really what I'm doing when I add shaded to unshaded, I'm having destructive interference of those waves. Up here I have constructive interference of those waves. You can also think of it really just algebraically. I'm adding a negative number in this region from the shaded orbital to a positive number of the same magnitude from the unshaded orbital. And so where these two overlap, the sum goes to 0. So the picture here looks like, you have to draw it underneath, here are the two nuclei again, but now in the middle of the two of them, the electron density goes to 0. So I end up with a picture that looks something like this. Okay. So what do I have? I have a molecular orbital. Here's one molecular orbital. Here's the second one. This one has a node in it. This node, I'm going to draw a dashed line where the node is. And this node is actually perpendicular to the bond axis. That means there's 0 electron density in the middle between these two nuclei. And then there's electron density on either side around the nuclei. And I've kept the shading here. Again, this tells you the sign of the wave function. Of course, these two regions, once you square the wave function and make orbitals back out of them, these two regions spatially look just the same. But this is just to remind us that there is a different sign and that this came from destructive overlap of these two 1s orbitals. This is also a sigma orbital. It has a node in it, which I showed you here, but that node is not along the bond axis. It's perpendicular to the bond axis. So here's the bond axis. An orbital that does not have a node along the bond axis, that has electron density there, is a sigma orbital. So this is also a sigma orbital. But we distinguish it from this one we drew here by the fact that it does have a node perpendicular to the bond axis. A node perpendicular to the bond axis, meaning no electron density right in the middle of what would be a bond, makes this an anti-bonding orbital. So that term is anti-bonding here. This orbital here, in contrast, is a bonding orbital. A bonding orbital has electron density between the two nuclei. It looks just like what we thought about as a sigma bond in valence bond theory. Electron density between these two nuclei, bringing the nuclei together to form a bond. An anti-bonding orbital has a node smack in the middle of where that bond should be. So the effect of an anti-bonding orbital is to push electrons out toward the separate nuclei, and as the name suggests, it works against bonding. Putting electrons in an anti-bonding orbital encourages the molecule not to form. All right, so we have two kinds of orbitals, a sigma bonding orbital and a sigma anti-bonding orbital, if we think about the overlap of two 1s orbitals like this to form, in this case, a hydrogen molecule. All right, so this shows you spatially where the electrons are in both a bonding and an anti-bonding orbital. I now want to talk about energetically where those electrons are. So before I erase this and draw an energy level diagram, I want you just to look at these two pictures and think about which of these is higher in energy. I'm actually going to stop the video or you're going to stop the video, and I want you to take however long it takes you, a few seconds, a minute, and think about which one of these has higher energy. And remind you what lowers the energy of the electrons that we're thinking about. What lowers their energy is interaction with the nuclei, right? And what raises their energy is interaction with each other. All right, so stop the video for as long as you need to, and come back when you have an answer about their relative energies. All right, so I'm leaving the picture of those orbitals up. So if you have the video back on now, you're ready to tell me which of these is higher in energy or lower in energy. It turns out the anti-bonding orbital here is higher in energy. The electrons in this orbital spend more of their time on the outsides of the molecule, away from the second nucleus. So remember, H2 formed because those electrons get the extra benefit of interacting with a second nucleus. In an anti-bonding orbital, they get much less of that benefit. So the anti-bonding orbital is higher in energy. And we can draw, might not surprise you, an energy level diagram to show this. So we have a vertical axis of energy, and we have down here lower in energy, the sigma bonding orbital. And because it came from overlap of 1s orbitals, we sometimes put a label on it. We call it sigma 1s. And then up here, higher in energy, we have the anti-bonding orbital. And so we don't have to write anti-bonding. We have a shorthand for that. We call it a sigma star orbital. And the star here means anti-bonding. All right, so now I'm going to erase these pictures. Here's our energy level diagram of the molecular orbitals. And we often like to draw these with reference to the atomic orbitals they came from. This is something called an MO, which stands for molecular orbital correlation diagram. And the way this works, it's actually sort of 2 or 3 diagrams in one. In the middle, so for this example, in the middle, we're showing the energy levels for the H2 molecule. And then on the sides, we show the energy levels for the H atoms that make it up. And those energy levels, there's just one that we're concerned about. It's the 1s orbital. And these should be at the same energy to start with. We show that this thing in the middle, this set of molecular orbitals, came from these 1s orbitals. We show that with dotted lines. This looks a little bit like the splitting diagrams, right, we had for d orbitals. We show that this comes from those. But just keep in mind, these things don't happen at the same time. On the outsides, we have the H atoms. On the inside, we have the H2 molecule. And our H atoms each had 1 electron in the 1s orbital. I'm drawing it very suggestively here. I'm going to draw this electron with spin down and this one with spin up because I know I want to put them together to form a molecule. You don't have to do it that way. But these are the atoms we start with. Each has 1s electron. And if we want to look at where the electrons are in the molecule, we fill up these energy levels just like we fill up energy levels for anything. We start with the lowest energy. We pair up when we can before moving to higher energy levels. So we have 2 electrons to put in our molecule, and we put 1 in here, and then we put the other one in there, and we're done. And so for H2, we have 2 electrons in the sigma 1s orbital. We can write an electron configuration for H2. And you'll see this sometimes, probably see this in your textbook. We don't honestly do this a lot, but you can. The electron configuration is sigma 1s2. So that looks sort of like an atomic electron configuration. It shows we have 2 electrons in the sigma 1s orbital. Both these electrons are in a bonding orbital, so not surprisingly, this is a molecule that stably forms a bond. So before we end this topic, I want you to try to answer one other question. So I'll ask you to stop the video again. I'd like you to take this correlation diagram and now apply it to helium. So helium, atomic number 2, has 2 electrons in it. Those electrons are both in 1s orbitals. So you can think about the molecular orbital diagram for helium as being very similar to the molecular orbital diagram for hydrogen. So go ahead and stop the video, and using this diagram, tell me what the electron configuration is for helium-2, the diatomic helium molecule. Okay, So if you're back now, you're ready to do helium. I'm going to just change the diagram I have. I'm going to make this helium on the outsides, and I'm going to form helium-2. I will now, for each helium atom, I'll start with 2 electrons in the 1s orbitals. And so when I fill up the energy levels in the middle for helium, I have a total of 4 electrons to put in here. And so I put in 1, 2, and then 3, 4. The molecular orbital diagram for a helium molecule, He2, is then sigma 1s2 sigma star 1s2. And you could have either written it out this way, or you could have just, the diagram here also works. It's not technically an electron configuration, but it shows you the electron configuration. So why did we do this example? There is no helium-2 molecule, and I think you knew that already. Helium's a noble gas. It doesn't form bonds with anything else. And you might have thought of this just because helium has a full 1s orbital, so why does it want to share electrons with anyone else? Molecular orbital theory just gives us a different way of thinking about that, which is to say, if you try to combine 2 helium atoms, you will form a sigma 1s and a sigma star 1s orbital. If you put the electrons in, you then have equal numbers of electrons in a bonding orbital, which encourages bonding, and in an anti-bonding orbital, which discourages it. And when you have equal numbers of electrons in both of those, there's no driving force for the molecule to form a molecule. So in fact, helium-2 does not form. So again, this is something you already knew, but MO theory gives you another way to think about this. And it gives you a way to think about it that will be very useful as we think about larger molecules with more and different kinds of molecular orbitals.